So failure under static load, and we said we're going to do a brief recap about stress component and principal stresses versus stress component, state of stress or stress element. So we're going to do a brief recap about mechanics of materials. So let's start. So we know for sure that the allowable stress is always the yield divided by the factor of safety. Deal. So whether ductile or brittle, we don't want material to deform, therefore to remain elastic. Okay. Maximum shear stress in this case. Maximum shear stress in this case. So we have the case study, maximum shear stress for ductile material. Okay, so this is the first one we consider. As you remember, we said before that we're gonna do maximum shear stress for ductile material and distortion energy. So we start with this one. Okay, it always says that the tau maximum is less or equal to tau y, which is the yield divided by the factor of safety, and we're gonna prove this later on. But I want you to pay full attention to this. Tau y or divided by the factor of safety for the case considered in a simple tension test, and tau maximum for the case considered. First, if you cut it at the right angle, we have a specimen, if you cut it at the right angle and we do tension to this, so the stresses available, the stresses component will be stress x while tension from horizontal, y vertical, and we have theta at 0 because it is lying on the axis. If you rotate by, in this case, if it is a simple tension test, as we've seen here, if it is a simple tension test, as we've seen here, so all what you have to do, well, in this condition, the sigma y equal to 0 and tau xy are equal to 0. If you rotate theta by 90 degrees, you might find out, that theta value in this case is equal 90 degrees. So we have sigma x1, sigma y1, and we have tau x1, y1. Okay, so the stress component, as we said before, we have the stress component sigma x, sigma y, and tau xy, and our objective is to calculate the principal stresses sigma 1, sigma 2, and sigma tau maximum in plane xy. Okay, so sigma x, sigma y, and tau xy, they are stress components, state of stress or stress element, and the distributions, they look like this. Tau xy are either approaching one another, as you see here, or they're getting further apart from one another, like in this case and this case here. So the stress formation, if we know sigma x, sigma y, tau xy in given orientation, we can calculate x1, y1, sigma, and tau x1 in any rotation at any angle. Okay, and the formula is very straightforward. So we have sigma x1, y1, and tau. In this case, the sigma is x1, y1, and tau xy, x1, y1. So if we have it at angle 0, we could calculate it at any angles we have. Okay, so the stress component, sigma x, sigma y, and theta tau xy, from it we can derive the principal stresses. The principal stresses are in this equation here, and we have here plus minus, so it's in a way sigma 1 equal a plus b, a minus b, and we have tau maximum are equal to those. Okay, in case we have and tau maximum equal plus minus sigma 1 minus sigma 2 divided by 2, bearing in mind sigma 1 is the highest and sigma 2 and the principal stresses are the lowest, are the minimum amount. I will see this as an example. Okay, so let's go back to the simple tension test. If we have a tension, we have sigma x only, we don't have sigma y in this case because it's a simple tension test, and tau xy in this case are equal to 0. So if with sigma y equal to 0, tau xy equal to 0, so those equation literally is equal to sigma x over 2, tau maximum, and maximum shear stress, as we've seen before, maximum shear stress for ductile material, we said tau maximum will be less or equal to sy divided by 2, tensile stress out yield point. Okay, so in this case we have sy is equal to sigma x. Okay, so the maximum shear stress for this